Hello and welcome to this 10th class in this physics of materials lecture series. In the past few classes we have developed the Drude model for materials and specifically applied it to the metallic systems and tried to see if we can make predictions of the properties of a metal. And we found that it has a very good capability of predicting some of the properties of metallic systems, and specifically in the last class we focused on what were the successes and the limitations or failures of the Drude model, where it was able to give us a good understanding of why something is occurring, and also where it perhaps gave us misleading answers, maybe even wrong answers. So this is the journey we have done so far. Like I said, specifically the thermal conductivity, the electronic conductivity are predicted correctly. The Weidemann-Franz law is also predicted correctly, but on further deeper exploration we find that the prediction for the electronic contribution to specific heat is actually overestimated. In fact, the actual contribution is much less, and the mean square velocity that it predicts is actually less than what is actually there in the systems. So this is something that we have seen, or at least we have stated this and come this far. So today what we will do, and today and in the next class or so, we will actually focus more on trying to understand why the model has had some issues addressing some of the questions that we find along the way. And what is it that is central to the problem that this model has. Okay, on a more macroscopic sense, we have, or on a more general sense, descriptive sense, we already understand that there are certain aspects of the material system that the model ignores. So for example, it is ignoring the interaction between charged particles, it is ignoring the interaction between the electrons that are running across the system and the specific positively charged ions that may be present in the system, at least in the sense that there is no accurate depiction of this interaction. There is just a generic resistive term that we throw into the system. So there are already issues even at a descriptive sense with this model, but still we would like to explore further to see if we can identify that specific concept or that specific idea that is very central to this model, which and which is not really appropriate for the system that we are applying it to. Okay, so that is the region of study that we need to look at and see if we can extract this information out of this model. So to do this, let us step back a little. We will put down some numbers. In some cases I have just told you that it does it gives us a value of approximately such and such for a specific property. We will step back and put those numbers down and actually walk our way through those numbers and then see if from somewhere there we are able to get some ideas of what is going wrong and where it is going wrong. Okay, so that is what we will do today. So if you look at the equations we put down for this model, first we had the electronic conductivity sigma, and we got that to be NF E square tau by m. Okay, so this is what we got. Then we got thermal conductivity K 1 by 3 V square, average of the V squares tau CVE, and also the CVE itself, because it comes from the kinetic theory of gases, the CVE is 3 by 2 NF KB, where KB is the Boltzmann's constant, and the average translational kinetic energy is 3 by 2 kBT for an electron. So these are some of the parameters that we have that are based on this model and all the assumptions that go into the model. So these are all the things that we got out of it, because we have just used kinetic theory of gases for this process. These equations which come from the kinetic theory of gases actually hold in the system and are also consistent with this model, and based on the application of these equations on other aspects of this model that we did in the last couple of classes, we got this expression for the electronic conductivity and this expression for the thermal conductivity. So with these expressions we will now spend some time trying to put together some numbers for them and then extract some information out of them. Okay, so first let us start with NF. We did this a little earlier, but we just redo it here so that we can make it complete for this current discussion. So if you take silver as an example, its density is 10.49 grams per cc per centimeter cube, and its atomic mass is about 108 atomic mass units. This works out very conveniently for us because the numbers are such that a factor of 10 would approximately take care of things. So let us look at the number of atoms per meter cube that we are looking at here, and assuming that silver behaves in a univalent manner, which it often does, then the number of atoms per meter cube is also the number of free electrons per meter cube. Fine. So this is what we have. So 10.49 grams per centimeter cube, or say let us say 10.5 grams per centimeter cube, is the same number of in meter cube it is into 10 power minus 6 is into 10 power 6 grams per meter cubes. Each centimeter would be 10 power minus 2 meters. So you have 10 power minus 6 meter cube in the denominator. So this is so many grams per meter cube. Okay, so so this is the same as in terms of number of moles per meter cube. We have 10.5 into 10 power 6 by 108 moles per meter cube, and if we assume that this is approximately a factor of 10 here, 10.5 by 108, so this is roughly equal to 10 power 5 moles per meter cube. Okay, so many moles of silver atoms are present per meter cube, and therefore if you assume univalent behavior of silver, that is so many moles of we can't really call it moles, but we'll leave it at that. The silver atoms would be then so many moles per meter cube, and this would amount to in terms of number of atoms per meter cube, we have 10 power 5 into 6.023 in 10 power 23, so approximately 6 into 10 power 28 atoms per meter cube. Okay, so the number of atoms per meter cube for silver at room temperature. So at silver, which is a good conductor of electricity, good conductor of heat and so on, at room temperature has about 6 into 10 power 28 atoms per meter cube, and I said that if it is univalent, we will have one electron being released per silver atom in the metallic system, and those electrons would then run around as free electrons. If you make that kind of an assumption, then the number of free electrons per meter cube, which is the NF value that we are looking for, NF is also the same 6 into 10 power 28 electrons per meter cube, free electrons per meter cube. Okay, so this is free electrons, free electrons per meter cube. So this is what we got for NF. So that is one of the quantities that we have there. So if you now look at CVE, the Boltzmann's constant Kb is 1.38 into 10 power minus 23 joules per atom per Kelvin. Okay, so this is what we have for the Boltzmann's constant. So if you look at CVE, this is 3 by 2 into 6 into 10 power 28 into 1.38 into 10 power minus 23. Okay, this is on a per atom. So if you look at the quantities we have put in here, this is the number of atoms per meter cube, or in fact electrons per meter cube, but since this is coming from the kinetic theory of gases, for the moment we can even treat it as atoms per meter cube, and later extend it and later just arbitrarily state that that is the same thing for electrons. So this is atoms per meter cube, this is the Boltzmann's constant in joules per atom per Kelvin. So if you run through this number, this is 1.5 into 6, so that is 9 into 1.38 into 10 power 5. Okay, so this is 9 into 1.38, that is about roughly about 12 and a half, approximately 12.5 into 10 power 5 joules per meter cube per Kelvin. Okay, so this is the CVE, that is the electronic contribution to the specific heat on a unit volume basis, and per unit volume we already saw that we have about 10 power 5 moles per meter cube for on a per unit volume basis. So this is the same as 12.5 into 10 power 5 divided by 10 power 5 joules per mole per Kelvin. Okay, so this is what your CVE will work out to. Okay, so at constant volume, the electronic contribution to specific heat at constant volume being extrapolated from the kinetic theory of gases. So this is what we end up getting. Now if you look at this value, so this is the value that we get. If you actually look at experimental data where people have and there are a lot of studies in the literature, you can actually go and look at it. Some of these are fairly old literatures from the even from the 60s and so on. You can see people have done very careful experiments where they have gone to very low temperatures and try to see what is the specific heat, and then try to therefore find out what is the electronic contribution to specific heat. So there is a lot of experimental data that enables us to do get this information. What we find is that the actual value is of the order of from experimental data is of the order of 0.2 or even less joules per mole per Kelvin. Okay, so it is of this order. Okay, it is less than about 0.2 joules per mole per Kelvin. So our theory is predicting about 12.5 joules per mole per Kelvin. The or the Drude model is predicting this, which is what we are currently following upon. The experimental values that you will find are about 0.2 joules per mole per Kelvin. So roughly about 2 orders of magnitude less. You can actually come up with exact numbers based on the system you are looking at and so on. The exact numbers and so on. If you look at it, it is roughly of the order of 2 orders of magnitude less. So this is the actual value is 2 orders of magnitude less than what we are predicting, or in other words the CVE is being over predicted. We are actually predicting a value 2 orders of magnitude higher than what is actually present in the system. Okay, so on the other hand we find that if you look at the thermal conductivity itself, we have 1 by 3 V square tau CVE, and so if you look at this, basically what is happening is that if you assume that the tau is being predicted acceptably right, which it seems to, then we have that the V square value is being actually under predicted, because this is being over predicted, and this is being under predicted by 2 orders of magnitude, similar magnitude. So we will also now so this is something that we note down, predicted is approximately uh, 100 times less than actual, by predicted by Drude model is 100 times less than actual. So incidentally, if you want to see what it is predicting, we have we just put down this half m V square is equal to 3 by 2 kBT. Okay, so at room temperature or thereabouts, T would be of the order of 300 Kelvin. okay, so roughly about 300 Kelvin we can say. So therefore V square equals 3 kBT by m. So if you put down the values, this is 3 into 1.38 into 10 power minus 23 into 300, and we divide this by 9.1 into 10 power minus 31, which is the mass of an electron. 9.1 into 10 power minus 31 kilograms per electron is the mass of the electron that we have here. So we have 3 here, 3 here and a 9 here, so they will approximately cancel out. So we have what we have is roughly, so V square is approximately equal to 1.38. We have 10 power minus 23 here and a 10 power 2 here, so 10 power minus 21 in the numerator and 10 power minus 31 in the denominator. The rest of them are constants which we just figured out, 3, 3 and 9 go. So this is 10 power 10, 10 power minus 21 by 10 power minus 31, so that is 10 power 10 meter square second square per second square. So we mentioned this in the class without specifically sort of deriving it or putting it together. So we find that the mean square velocity is of this order, okay, and based on what we are understanding now, this is actually being under predicted by 2 orders of magnitude. So this is something that we will look at. So we will just keep this information in mind for the moment. We will come back to it a little later in the class. Right. So we just looked at mean square velocity. Okay. So I also wanted to I am putting down some values here because it is going to lead us into understanding better what is the problem that we have faced with this model, but also to give you an understanding of what are the different aspects that we are dealing with here. And specifically with respect to velocity, we have something that we need to be careful about, or at least alert to. So the other velocity that we mentioned is the drift velocity, okay, and that was in the context of the electronic conductivity calculation that we did. Okay, so we calculated something called drift velocity. So now let us try and see if we can come up with a number for this drift velocity. Fine. So again we will take the example of silver because it is a very good conductor, and on that basis we will see if we can come up with some value for drift velocity. So what we see is, so if we take silver, the parameter that is now of interest to us for our immediate discussion is its resistivity. So I just let me start by putting down its conductivity value. Sigma is about 6.3, this you can into 10 power 7. I just looked this up in a database. Any book, many books will give you a value, so you can easily look this up. The other values I have put down are also values that you can find in any standard book. Okay, so the atomic mass of silver, the density of silver, the conductivity of silver, resistivity of silver, and of course the other constants, Boltzmann constant and so on. So these are all things you can look up, and so I have looked this up somewhere. So this is the value that you have, 6.3 into 10 power 7 ohm meter inverse, and of course it is one of the best conductors that you can find incidentally. So this is one of the best values that you will find for conductivity in a metallic system. So this is what we have. So we will assume that we have a 1 meter length of wire of silver, and let us say its diameter is 1 millimeter. Okay, so we have and this is not far fetched. You can have a 1 meter long wire which is 1 mm in diameter. Of course if it is silver, that is an expensive wire, but this is just for our discussion, and you can certainly buy such a wire. It is not so expensive that you cannot buy one, but anyway the point is you could use such a wire, and you could easily certainly find one such wire, and it serves for our purpose of discussion, so we will follow up with it. So let us start by seeing what is the resistance of this wire. Okay, so resistance R is rho L by A. Okay, L is 1 meter we have got, A we have to get for this diameter, and rho is simply the inverse of conductivity. Okay, conductivity is whatever it is, this value here, the rho is inverse of this. So this is actually 1 divided by the conductivity, which is 6.3 into 10 power 7. Area is pi d square by 4, so we will have into pi. D square is this is in millimeter, so this is 10 power minus 3 meters, right, 10 power minus 3 meters. So d square is 10 power minus 6. Okay, so that is pi d square divided by 4. So this is what we have here. So let us just work this number out. So this is 4 divided by 6.3 into pi, or 3.14. Okay, and we have 10 power 7, 10 power minus 6, so we have 10 in the denominator effectively, okay, into 10. This is roughly 0.8 times, this will go up roughly 0.8 times, and if you multiply 6.3 by 0.8 you will roughly get 5. Okay, so approximately we are only looking at approximate values here, 1 by 50, 1 by 5 into 10, so that is roughly 1 by 50. Okay, so resistance is 1 by 50 ohms. So this is what we are looking at, R is equal to 1 by 50 ohms. Fine. So this is the resistance of a silver wire that is 1 meter in length and has a diameter of 1 millimeter. This is the resistance. So we will just apply a 1 volt potential across it. So these are all numbers that are very reasonable numbers. Okay, so these are all I mean very doable. I mean you go buy a battery in a shop, it is 1.5 volt battery. So we could easily arrange to have 1 volt put across this silver wire. So we will just put 1 volt across wire, across length of wire. Okay, so then we have V equals IR, Ohm's law. R we know is 1 by 50 ohms. Okay, so if you want you can put it down specifically, it's 0.02 ohms. Okay, so 1 by 50 ohms is 0.02 ohms. So V equals IR, therefore the current through the system I is simply V by R, which is equal to 50 amps. Okay, so we now have so effectively if you take a 1 meter long silver wire with 1 mm diameter and you just put 1 volt across it, you will get you will support a current of 50 amps, and 50 amps by the way is a lot of current. Okay, in fact it's a lot of current, so you may have a lot of heat from it and so on, but this is the basic calculation. The calculation shows you that it will try to support 50 amps. It is electronically it is capable of supporting 50 amps at this point because of the voltage that you have placed across it, right. So now 50 amps, so when you talk of current, that is basically transport of charge. Okay, so current times time, that is charge per unit time is current. Okay, so charge per unit time is current. So therefore if you look at if you write, you can write it this way, I times T equals Q. Okay, so the charge transported per unit time would be, or per charge by time is the current, or similarly therefore current into time is the charge, right. So this is the situation we have. Now the time that it takes for we will assume that the electrons are moving with this drift velocity, which we do not know at this point what that value is. We will assume that the electrons have a drift velocity okay, some v final, so that is the drift velocity, fine. So the time it takes to go across a length L of that conductor, time taken Okay, so time taken to travel distance L is simply L by Vf, so that is the time taken to travel that distance. So okay, so we can now substitute that back here, which we will do now, right. So we have the current I into L by Vf, this is equal to the total charge that is getting transported, okay, across as a result of the passage of that current. Now what is the total charge? That total charge is the number of free electrons, because they are all getting transported as a result of this this is number of free electrons per unit volume times the volume of that sample, which is the cross sectional area of the sample into the length of that sample, okay. So this is the volume of the sample, this is the number of free electrons in that sample per unit volume times their charge, okay. So this is the total charge that is present in that system in the form of the free electrons, okay. The free electrons possess this much amount of charge, and when you say current is passing through, then this is what is getting transported, okay. So that is the total charge, and because it has to maintain charge neutrality, so whatever is getting transported has to be transported back in. So this is what is the situation. So if we simplify this, we have these two L will go, so we have the drift velocity Vf is simply I divided by Nf, the cross sectional area A, and the electronic charge E, alright. So now let us put the numbers back into this equation. We had the current being 50 amps, right. Nf we said is about we just came up with 6 into 10 power 28 electrons per meter cube. The cross sectional area is pi d, so this is about 0.8 into 10 power minus 6, this is pi d square by 4, so pi by 4 will be 0.8, and the d square will give you the 10 power minus 6 into the electronic charge 1.6 into 10 power minus 19 coulombs, right. So now let us just simplify this. So this is basically you will have actually this 6 times 0.8 is about is roughly about 5 you can say, and so that will become 10 on top. So we will have we just put it down, this is approximately 50 divided by the 6 and 0.8 would become roughly about 5. We have 10 power 28, 10 power minus 6 and 10 power minus 19. So these two would become 10 power minus 25, okay. So 10 power minus 25, so and 10 power 28 we have, so 10 power 3 we will have, minus 25 and 28 will give you 10 power 3, and you still have 1.6, okay. So this is roughly 50 by 1.6, I am sorry 10 by 1.6, so 10 by 1.6 into 10 power minus 3, and so this is actually about 5, no it is about 6, sorry, so 6 into 10 power minus 3 meters per second, okay. So 6 so this is 6 into, so this is Vf, six into 10 power minus 3 meters per second. So this is actually what when if you look at this in millimeters per second, this is only 0.6 millimeters per second, I am sorry 0.6 centimeters per second, so 6 millimeters per second. Okay, so we see that the drift velocity is 6 millimeters per second, right. So this is not a large number, this is a very small number, fine. So in fact if you look at it, let us say if you look at this board, the length approximate length here is about 1 meter, okay. So roughly about 1 meter we can say. So if you think of some simple circuit that we can draw, so let us just say we have a battery here and we have a wire, a silver wire at that, and a bulb, and the wire comes all the way back, and we have a switch somewhere here, okay. So let us say we have this hypothetical circuit which we could very easily set up, and let us say we have access to some fairly expensive silver wire, 1 millimeter in diameter, 1 meter in length. Actually we would need 2 meters, we would need 1 meter to get to the bulb, 1 meter to come back. So now let us say we close this switch, okay. So now there are electrons all over this silver wire, it is charge neutral, so they are not really I mean we are not losing electrons anywhere, we just close this switch. If you see, given that and let us say we have just put 1 volt here, okay. So 1 volt is what we have put, let us say, and so we have now we have a circuit which is consistent with all the calculations that we have done. If you close this circuit, you see that this 1 meter length, if it has a drift velocity of 6 millimeters per second, okay. So it is basically 1 meter by 6 into 10 power minus 3 meters. So the time that it will take is about 150 seconds or more, little more than 150 seconds for the electrons to actually travel this distance and reach the bulb, okay. So 150 seconds is a lot of time, it is 2.5 minutes, right. I have actually walked across the board here, I have barely taken a second or two to come to this side of the board. It will take 2.5 minutes from the time you close that circuit for the electrons which are close to that switch or close to that battery to come all the way up to this bulb, if you say that this is the drift velocity, right. So this is something that we have to really be I mean we should become aware of. When we close the switch, the light comes on instantaneously, okay. So we do not see any difference, I mean we switch it, we close the switch and we just do not know the difference, almost immediately the light is on. But if you go into the details of the system, we find that electrons at one end of that system may take this long, of the order of 2.5 minutes under the circumstances that we have just described, for them to actually complete to reach the bulb and actually participate in this process, fine. So in fact what is actually happening is because of continuity, the electrons which are very close to the bulb start burning the bulb to begin with, and then the other bulbs the other electrons arrive at the bulb. So this is basically the process that is occurring, but I want you to get a sense for the fact that this number is rather small, okay. So even if you are actually in fact, to draw an analogy from daily life, if you are actually watering plants with a hose and then you have water coming through the hose, the velocity of water inside that is going to be higher than this. So when we think of electronics and we think of how instantaneously things occur and so on, if you go into some details you find numbers like this which are very surprising in this context, in the context of what we normally associate with electronic processes, okay. So this is a very small velocity, the drift velocity that we have come up with. Incidentally, if this is the drift velocity, we can also work out a value, and I would also like to draw your attention to the fact that this drift velocity is actually just to the extent that it is a small number, it is very therefore drastically different from the mean square velocity that we previously discussed, okay. In the mean square velocity calculation, we came up with a number of 10 power 10 meter square per second square, and even that we said is actually an underestimate of the velocity. So what is the difference here? Please remember, when we talk of thermal conductivity, when we talk of thermal conductivity, there is no the electrons are not going anywhere, so to speak, only heat is being transferred from one side to the other side, okay. So and that is occurring by the collisions of those various electrons with each other, okay. On the other hand, when we talk of electronic conductivity, you apply a potential and there is a continuous movement of electrons are entering one end of that wire and exiting the other end of the wire, okay, and there is a loop and they come back, but the process is there is a movement, there is a net movement of electrons. So if there is some way in which you could follow them, you find that there is a net movement of electrons. So there are two things that are occurring, given the temperature of the system, let us say room temperature or any other temperature, the electrons are all randomly moving, okay. So they are randomly moving about very rapidly, they move about very rapidly, they bounce off of each other and so on, but their net velocity is 0, they are not headed anywhere overall on average their net velocity is going to be 0 because they are largely going to stay within the system, they are not headed anywhere. But if you actually look at the average of their speeds or average of and therefore the average of the square of the velocities, that is going to be a very large number, because at a given instant it has a very large speed in some particular direction. So if you take that number into account, it is a large number, but overall they are not going anywhere. So overall if you look at it, it is essentially stationary. When you apply a field, in addition to this high speed random motion that is going on within the system, in addition to that we have an overall drift of the electrons. So that overall drift of electrons is this drift velocity. So therefore it is now that we recognize this, it is no longer that surprising that within the system we have a very high speed random motion going on, which results in this high average v square value, but the average drift of the electrons over and above this random movement is actually a very small number. So therefore these are two different numbers, so in these derivations we have walked through them at different points in time. I just wanted to highlight that that there is a difference. And now having come up with this drift velocity, we can also put down a number for that mean time between collisions, which also we previously just randomly arbitrarily put it down and gave some value for it. We can actually, given this value, we can actually come up with a number more appropriately. So we will do that. We see that the Vf is 6 into 10 power minus 3 meters per second, okay, and tau, the mean free time between collisions, is mVf by EE. This is how we defined it. This is how we saw it in the equation that we derived a couple of classes ago. Okay, so this is what we have. So if you look at our system here, this is m is the electron mass, so that is again 9.1 into 10 power minus 31 kilograms. Vf is this value that we have here into 6 into 10 power minus 3 meters per second. The electronic charge is again known, 1.6 into 10 power minus 19 coulombs per electron. This field that we have put 1 volt across a length of 1 meter, so it is 1 volt per meter, which is that field that we have, so into 1. So this is all we have in the system. So now we can run through this calculation. This is 10 power minus 31, 10 power minus 3, so this is 10 power minus 34, and we have 10 power minus 19 down here. So if you bring this up here, it will become 10 power plus 19. Okay, so so this is equal to 9.1 into 6 by 1.6 into so we have 34, so 15, 10 power minus 15. Okay, so 1.6, so 10 power minus 19 will become plus 19, so this will become plus 16, so we have minus 15 there. Okay, so this is what we have. So if you work this out, this is roughly 4 times roughly, so this is roughly about 49, so about 35 or 3.5 into 10 power minus 14 seconds. Okay, so mean free time between collisions is 10 power minus 14 per second, is 10 power minus 14 seconds, and that is the order of magnitude that we mentioned earlier when we were doing our discussions. And incidentally, I also wanted to point out that you know, if you put a larger field across the system, then accordingly things will change. You may have higher currents and so on, so some numbers may change here and there, but these are numbers that we can say are the right order of magnitude. This is the kind of number that we mentioned earlier also. So all these numbers we mentioned earlier, we didn't really put them down, and I didn't show you how they came about. So today I have taken the time to show specifically how these numbers come together, so that we can relate to them much better. So that is the way these numbers come, or at least one way in which we can arrive at these numbers. Okay, and we also have been discussing through the day about how reasonable they are and what the error is. So as far as the Drude model is concerned, we have looked at all the major results of the Drude model, come up with numbers. In one case looked at the fact that experimental values are distinctly different from the theoretical prediction, and that is one thing that we noted, 2 orders of magnitude off and so on. So with this feel for the Drude model and the expressions it gives us, the values it predicts and so on, we will examine it a little more to see with also this understanding that the Drude model actually succeeds in some places and fails in some others. With the help of these equations and these numbers, we will examine it a little bit more to see if we can get a better sense of what is that particular aspect of the Drude model where the error lies, so that we can then examine that aspect some more and find alternate ways in which we can address this situation. So we will do that now. Okay, so if we put it down now, we have 2 places in the Drude model where we specifically have issues with what it predicts. One is the electronic contribution to specific heat at constant volume, and the V square value. Okay, so this v square value, then I mean we talk of half m v square as being the translational kinetic energy of an on a per electron basis. This is also energy and how that energy changes as you change the temperature. So this is so we find both of these are related to energy, okay. So they are somehow related to energy of the system, and this velocity that we are talking of, we have actually put this down as the mean of the squares of the velocities, because we said that that is more representative of a system where you have so many 10 power 23 order of magnitude kind of electrons. So what we need to understand, what we need to recognize from this situation is that somewhere along the line we are using some process by which we are coming up with this average for this v square, which is possibly where there is an error, okay. So because that then gives us the energy, then and essentially that all relates together here because it is all related to energy, fine. So this gives us a clue that first of all the issue is with how we are estimating energy, how we are estimating the behavior of the energy of that system, behavior in the sense of this how much more energy would you require to raise the energy of the system by the temperature of the system by 1 degree and so on. So all that relates to how is energy present in that system, okay. So that is the key question that we are trying that stumbles out of this look at what the Drude model has done and what it has predicted. So somewhere along the line in our description of this model we have made some assumption about how energy is held within the system, and that assumption is affecting us later on in the predictions that this model is making, fine. And as I said before, this model starts using the kinetic theory of gases as its basis. So the manner in which energy is held within the system is the same manner in which energy is held within the system as it is indicated in the kinetic theory of gases, okay. So that is the link that we have, right. So in the kinetic theory of gases, okay, there is a statistical distribution, statistical description, a description of the manner in which energy is stored within the system. In the kinetic theory of gases as well as in the Drude model, where we are dealing with a very large number of particles, very large number of particles, it is not feasible, it is highly infeasible for us to actually know the energy of every single individual particle. So even when we talk of a v square value here, average of the squares of the velocities, it is not actually calculated by somehow having a detector which actually now measures the velocity of every single electron or every single molecule present within the system, and then somehow you know that you add them all up and divide by the number. So this is not something that we can actually physically do. Instead what is actually done is a statistical method is adopted, where we make some assumption on how the energy is distributed amongst particles, okay. That assumption is not, I mean it is based on what we understand of the system. Based on what we understand of the system, we actually come up with this description of how energy will be stored, how energy will be distributed amongst the particles. You have a very large collection of particles, you have some energy. Now all the particles do not attain exactly the same energy at exactly the same time, so there is a distribution. So some assumption is made on how that energy is distributed, or a theory is built to tell us how that energy is distributed amongst those particles, okay. So that theory in the original kinetic theory of gases has been built for this large collection of ideal gas molecules, okay. So ideal gas molecules, non-interacting ideal gas molecules is that system that has been taken up for discussion or description, and in that system, given the manner in which those ideal gas molecules behave, okay, given that understanding of how ideal gas molecules behave, based on that understanding a description has been developed on how energy would be stored amongst those particles, okay. So that description is referred to as the Maxwell-Boltzmann distribution. So the Maxwell-Boltzmann distribution, okay, so which is attributed to these two people, Maxwell and Boltzmann. Maxwell-Boltzmann distribution is a fundamental aspect of the kinetic theory of gases. In the kinetic theory of gases, where we come up with v square mean square velocity, that mean square velocity comes from as a direct result of the Maxwell-Boltzmann distribution, and the Maxwell-Boltzmann distribution merely looks at this specific case that you have this large collection of particles, of large collection of non-interacting particles, and then tries to explain how energy would be distributed in that system. In other words, at a given energy how many particles would be there, at some other energy how many particles would be there, and so on. Okay, and what is the logic based on which this distribution is occurring. So all of that is put together in this Maxwell-Boltzmann distribution. If you look at the Maxwell-Boltzmann distribution in detail, from the Maxwell-Boltzmann distribution you can come up with a velocity distribution. Okay, so there are two things here, a Maxwell-Boltzmann distribution which shows you how the energy is distributed. From that you can extrapolate and get how the velocities are distributed, or therefore how the squares of the velocities are distributed. Okay, and so from there we get a value for v square, this average of the squares of the velocities. So this is therefore the energy of the system, how things are distributed, how energy is distributed within the system, and therefore something that affects your CVE calculation, how and specifically how it affects your v square calculation, mean of the squares of the velocities, are directly related to how the Maxwell-Boltzmann distribution describes the distribution of energy within that system. So this is very fundamental to the kinetic theory of gases. Okay, and to the extent that we have extended the kinetic theory of gases and imposed the rules of kinetic theory of gases directly onto the free electrons that are present within the wires or the metallic systems that we are looking at, to that extent in the description, even though we so far did not explicitly state it, what we are effectively stating is that electrons within a solid, the free electrons within the solid, are actually following Maxwell-Boltzmann distribution in terms of how they are distributed amongst the various energy levels that are available to them. Okay, at this moment I am just indicating it to you as energy levels and so on. In our next class we will discuss that in greater detail, so it will become more clear to you. But the point is, the point I wish to highlight is that there is such a thing called Maxwell-Boltzmann distribution, which looks at how energy is distributed within the system, from which you can get a lot of things out of that system in terms of, for example, the velocity distributions and so on. And the Maxwell-Boltzmann distribution is valid for a set of non-interacting particles, but there are some other specifications too which we will get to, and therefore it is perfectly valid for this ideal gas system, which then and therefore perfectly valid for the kinetic theory of gases. We have taken this distribution and imposed it without necessarily stating it upfront. We have imposed it on the system of electrons present within the within a solid, which and therefore ensured that, you know, or at least therefore use this idea that their energies and therefore their velocities are also similarly distributed. Okay, so we have imposed this idea onto those electrons, and as a result of which the numbers that we have come up with, we came up with some numbers for CVE and V square and so on, and it turned out that those numbers were wrong. Okay, so somewhere along the line the use of this Maxwell-Boltzmann distribution for the electrons has turned out to be incorrect. Okay, so that is the underlying message that we are now able to extract from all the understanding that we have now come up with in this system. Okay, so something that was valid for non-interacting particles, we have imposed on particles which can actually interact with each other. Electrons can repel each other, electrons can get attracted to the ionic cores. So we have imposed this on those particles, and it has turned out that it is not really correct. It is giving us 2 orders of magnitude error here and 2 orders of magnitude error here. So so therefore that is the so there is an error in imposing this. Okay, so what we will do in the next class is we will look at this distribution in greater detail, and we will actually derive this distribution. We will look at all the assumptions of this distribution and derive this distribution in the next couple of classes, and we will see that and we will see what that prediction is. Okay, and then what we will find is that I kept mentioning that these are non-interacting particles and so on. There are specific assumptions made on the behavior of a particle, which allows us to use Maxwell-Boltzmann distribution to describe its energy. We can't use this distribution to describe the energy of just about anything we wish. The kinds of particles that only particles that have certain attributes can be reasonably made to follow, I mean can be reasonably expected to follow the Maxwell-Boltzmann distribution. Fine. So what we will see is the kinds of particles that actually follow Maxwell-Boltzmann distribution are referred to as classical particles. Okay. So I have now given you two terms to think of, Maxwell-Boltzmann distribution and classical particles. Okay. This is something that you will hear mentioned in many places, many books will mention classical particles and so on. What we will do specifically in the next few classes is we will look at this, we will derive this Maxwell-Boltzmann distribution and understand our sources of error. So therefore that is itself an immediate task that we have ahead of us, and by doing the derivation and understanding the sources of error, we will also see if there is a we will see if there are pointers on where we should head to see if there is a better way of describing the system that we are dealing with. And in that search for a better description for the manner in which the particles in the system that we are dealing with, the electrons in a solid, in that search for that a better description for those particles, we will actually focus on this definition of what is a classical particle. Okay, so we will look at this distribution, and as a result of having of what we understand from this distribution, we will come down to this specific term classical particle, which is often in many books is just mentioned. We will actually analyze this description, the definition of a classical particle very carefully. We will see what is the kind of a particle that gets called as a classical particle and what is a non-classical particle. Okay, what is that specific feature that distinguishes between a classical particle and an electron, for example, specifically in our case, since we are dealing with electrons, what is it that is different between a classical particle and an electron, and therefore if Maxwell-Boltzmann statistics can be used for classical particles, what is the other description that we could possibly use for electrons. So this is the direction in which we will head. Once we identify this other description that can be used for the electrons, we can then go back and redo our equations and see if we are now in a position to better make predictions, and specifically if we can correct for these errors, specifically the errors in the specific heat capacity at constant volume. So this is the direction in which we will head. We will look at this distribution and look at the definitions and come up with a new distribution. So with that we will halt in this class, and we will take up these issues in the upcoming classes. Thank you.